let's say what? 1, 5, 3. Let's go. So 1 goes here, 5 goes here, 3 goes where? Huh? And then if I have here a 7, and then if I have a 4, and if I have a 2, and now suppose I have a 9, 9 goes here, and if I have a, now suppose I have a 3.5, or even a 2.5, where is this going? I cannot put it here, so I put it here. So the solution, that's the only thing I have to say about it, relies on taking an array and building those sorted stacks, if you like, right? You see how this corresponds to the array in the sense that for every number, I figure out to what stack can I put it on as left as possible, right? So this 2.5, I couldn't put it here because that would break the order of the stack, so I put it here. If I have here 1.5, where would that go? Right here, right? And then from this, you build a solution. Now, this is a problem in your next, one of the dynamic programming homeworks. It's 15.4.6 that says, how can you do this efficiently? So 15.4.5 just shows it's dynamic programming. But if you do this particular organization of dynamic programming, you get a more efficient algorithm. Okay? So where are we? Dynamic programming. Let's recap the parts of dynamic programming, which are so that's what we've done so far. Then what do we have next? Part 2. later on. So we talked about this dependency, so subproblem dependency. Later on, we see this is a DAG. We don't know what a DAG is yet. Maybe you guys do. But later on, we're going to see that this has to be a DAG for the whole thing to work. If this graph has cycles, it would be hard to solve one problem before solving the subproblem, because I always have some subproblem in the cycle that I didn't solve. Yeah, so to be able to start from somewhere. Right? So that usually implies a solving computation order. If I know this table, I'm going to know which problems or subproblems I have to solve first, so that when I get to this problem, I want to have the subproblem solved. Part 3, bottom-up computation, following this order table. This is non-recursive. Next week, we're going to do something that's called memoization. That is a recursive version, recursive computation. But for now, part 3 will be bottom-up. That is non-recursive computation, solving all the problems in this table in the order I need to solve. And part 4 was trace solution or print. You can add part 5, runtime analysis. That's dynamic programming. The C is reserved. C equal objective is required. You're going to lose points if you use other letter than C. That would make it easier for us to understand what you are, and also clear for you. C must be the objective. So C takes a problem and returns the minimum or maximum, whatever the value objective is. In a knapsack, it's the maximum value. In the activities problem, is the number of activities. In the checkboard problem is the what? Minimum penalty on the path, and the coins, minimum number of coins, right? And at trace, we're going to insist that S of a problem is the trace. So tracing typically means which subproblems I need. So that typically means which, it's some kind of indicator which subproblem is being used. For each problem, trace should tell me what subproblems I need to solve. I'm not saying that's always the case. I'm saying in general, by trace we mean if we solve this problem, we got an objective, so many coins. Tracing meaning saying which subproblems did you use to get that number of coins. And that's also required. You are not required to use an S, but if you use a trace, it has to be S. When the TAs look at your paper, C and S has to stand out as the objective and the tracing. Okay, so that's kind of an overview. Those parts will be required when you write the dynamic programming solution. So you're going to have to do 1, 2, 3, 4, 5. When we grade your exam, we look for part 1, part 2, part 3, part 4. These, we don't want to be formal about runtime analysis. It's like before, it's like in sorting and all these other problems. We want to know how you think about it. You can think from pseudocode. Once you write the pseudocode, so this is pseudocode here. This is also pseudocode. Once you write it, the runtime analysis is no different than any other algorithm. We look in there, we see 2 for loops, that's in square, so on and so forth. So it's informal, but it has to be explained. So I have more dynamic programming problems for today. Kind of easy, all of them. So let's move on. We have, I think, so far 2 examples, right? We did, which is the coin problem and the checkboard problem. So how how about this rod cutting problem? So we have a piece of wire or something, you know, that's the rod, that has size N. And these are we can cut it in, so we can cut the wire and sell it with the following prices. There is a length and there is a price. So if I have 1, 2, 3, 4, 5, 6, 7, 8. Say the prices are not proportional with it's like in Home Depot. You don't get proportional prices with the length of the wire that you cut. So this is say 1, 5, 8, 9, 10, 17, 17, 20. If I have n equal 8, what's the optimal to do there? How do I get the most money? So the objective is maximize value, which is the sum of the prices. I want to cut this n equal 8 into parts to get the maximum I can. I want to maximize those things. Of course, it's like a knapsack. I can't get more parts than 8. If I choose to cut, say, a 3, and I choose to cut then a 4, then I have 1 left. So what's the maximum I can get? What's the maximum?
22.
22 how?
6 and 2.
6 and 2. So this is saying this the maximum value is 22. That comes from 5 plus the 17. The 5 comes from a 2 piece and the 17 comes from a 6 piece. Right? What if I change the price table? I add different, this is price 2 version, sale. Say I make this one a 3. 3, 5, 8, 9, 10, 17, 20. Now what's the maximum I can get?
23. 24. 8 3s are 24. 8 3s are 24.
Right. So in this price table, let's put this here. This price would be a 22, right? But from this price table, the maximum would be 24, because that's a 3 times 8, and 3 corresponds to the 1 piece. If I cut this rod in 8 pieces of 1 times 3, I get $24. So is this, the price table is given. It's not necessary to have all the possible lengths. Like this is, like in Home Depot, you can get 1 feet, 2 feet, 3 feet, 4 feet. But sometimes some price is not listed, right? There's no piece of size 4, maybe. So in general, for n, is this a greedy problem or a dynamic programming problem? Can you make a decision how to cut this wire without solving some problems? So let's look at part 1, which is saying given an optimal solution. So given this part 1, you always assume you have the optimal solution. Or you could, if you don't want to think that way, you could think, what would I do if somebody gives me the optimal solution? What kind of properties would it have, right? So if somebody shows me the optimal solution, it's what? How the optimal solution looks like. This is n, right? My rod. And it's cut into parts, right? So this is one of the lengths, right? There is length 1, length 2, length 3, and length 4. And those are the parts. The lengths have to sum to n, right? The sum of Li has to be n, because I'm cutting the wire. Maybe, again, if I wouldn't have those nice integers, in this problem, if n is an integer and I have the integers here, including 1, I'll never have something that's like wasted, right? Why? Because if I cut integers out of integer, either I get to 0, or I have some integer left. As long as there is a 1 with a price on it, I'm going to sell the remaining wire. But sometimes, if there is no 1, it's possible to cut it to get a maximal value and have a 1 here or something that's not possible to sell, right? So sometimes there might be a waste. But the way this is formulated with a 1, there is no waste. And the value I get is the sum of the prices on Li, right? If I cut the wire this way, the price of this plus this plus this is going to give me the what I can sell the wire for. So how do I characterize this optimal solution? Where should I imaginary break it so that I obtain some problems? Between the cuts, right? If I put this imaginary boundary here, I don't know where the boundary is because I have to know the parts that are being cut to decide the boundary, right? But if somebody gives me the solution, then I know the parts. I could say, if I cut it here, or here, or here, anywhere between those parts. Let's just do one cut. Say I cut it here. This has to be optimal for this part of the wire, and this has to be optimal for the other part of the wire. Right? So if I make the decision, it's a boundary between cuts. Between pieces. The left and right subproblems. So if I cut it here, this is the left subproblem. This is the right subproblem. Have optimal solutions given by the whole optimal solution. In other words, I take this solution, L1, L2, L3, L4. If I cut it here, the road, I say I have two parts, solve this problem, solve that problem. This L1, L2 must be optimal for this part, right? Exchange argument. If they're not optimal, if there's a better value that you can get, you would cut it that way, put it together, then you get back a better solution. Right? Same thing for that side. And I wanna do this anywhere I cut this between the pieces. This happens, right? I choose to cut it here, but if I cut it here, the same thing must happen. If I cut it here, the same thing must happen. And the other thing is, if the subproblems have optimal solutions, so if I have solutions for the subproblems that are optimal, if somebody tells me this is the magic cut, right? So now I don't have the solution. So this is the part 1B. No, I guess this is still part of 1. So I could put it there. I think last time we wrote it as 1A, 1B, and 1C, maybe. Let's do that. C, 1B. So that's part 1B. Let's make it more clear what the statement is here. In part 1b, I don't have the solution. So not given optimal solution, but I'm given only what? I'm given what? The decision. But given the decision, sometimes this is called split because it's split into subproblems. So now imagining I have my rod or the wire of size n, I do not see the optimal solution. What I'm given, if somebody tells me you need to cut it here, that is the cut that you need to do. In other words, somebody splits it into subproblems for me, right? It says, deal with this part, and that's the cut you need first. So if I have that, do I have the fact that the optimal solution, so then the optimal solution can be obtained by combining the subproblem solutions. So in other words, if somebody gives me this decision, and that's correct, it tells me if you solve this problem optimally, and if you solve this problem optimally, you put it back together, you get the solution for the whole problem. Right? Is that true? So what do we actually want to say here is that we're not trying to found the decision boundary here. But we want to say there exists such a decision boundary. Now somebody has to give it to me for this to work. I'm not going to find it right here. But there is one magic boundary that if I have it, I could just solve the subproblem. In this particular problem, the rod cutting, what is combined? What is this step is going to do? Assuming somebody gives me a decision, I go ahead and solve the subproblems. What does putting it back together mean?
Adding the
Right, but it doesn't mean any additional effort, just sum up the parts, right? It's just saying the solution from here plus the solution from here is the total value you have. In some problems, the combination is actually some algorithm step like in merge sort. Combination is not as just concatenating the results. You have to do something. So this part says, if you see the optimal solution, there is a way to split it such that the left and right are optimal. Now that's assuming you actually see the parts. This part is saying, now that there is such a split, which I don't know where the boundary, where the decision breakup is, but I know there is one. And if somebody would tell me which one it is, all I have to do is solve the parts. Because solving the parts will give me an optimal solution. Now, not all problems have this kind of structure. So we're talking about greedy versus dynamic programming. Both greedy and dynamic programming have this property that the optimal solution can be divided into subproblem optimal solutions. And if you know how to divide them, solving the subproblems gives you, via a combination step, the optimal solution. Okay? How do we call those problems? Somebody? Divide and conquer. Not all problems are divide and conquer. I gave you a trivial example a week ago or so. 3-SAT problem. That is, everybody knows 3-SAT? 3-SAT is a bunch of Boolean literals grouped by 3, like A or B or C, right? And not A or E or not E. And so all classes are of 3 literals. Those are Boolean variables. And you have to satisfy all of them because n between them. So one of these 3 must be true, one of these 3 must be true, one of these 3 must be true. How many people have seen this problem before? Hands up so I can see them, please. Oh, you guys absolutely must know this problem. If you want to graduate as a computer scientist, even from college, you have to know what 3-SAT is. So these are Boolean variable, true or false. and each clause have to have one of them satisfied, right? Because or, it means I have to satisfy one of them. And that means satisfy each clause, right? How about 2SAT? What's the difference between 3SAT and 2SAT? Right, this would be A or B, and maybe not B or C, and maybe not C and not, or not D, a bunch of legals. Same problem, you have to satisfy every clause because there's an or between them, and an and between clauses, you have to satisfy all of them. So if I give you one of these problems, 3SAT or 2SAT, how do you solve it? Can you impose this kind of structure written here on 3SAT? Can you say, okay, somebody gives me a solution, right? An optimal solution. I can break it into sub-problems to say, if this is an optimal solution, there is a sub-problem with an optimal solution on the left, and sub-problem on the right, and by solving them, putting back together, I get an optimal solution problem, da 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 da. No, doesn't work. So my point is, these kind of problems where I can do a breakup and divide into sub-problems, solve the sub-problems, and then put it back together, could be either greedy or dynamic programming. Greedy is when I can make this decision without solving left and right. Dynamic programming is when I have to solve a bunch of sub-problems to decide what the decision is. But not all problems have this structure. By the way, some variation of those happen in the meter before. Just to let you know. And most people said optimal solution structure, this is how we solve it, after I told them in class. This is not a divide and conquer problem. Anyway, just a hint. Okay, so that's part one here. How many people with me on this rat cutting problem? Optimal solution structure, we get that? Right. So 1C is, for now, you can treat 1C as a guess. You don't have to argue this with me. I mean, you have to argue it one way. If you say yes, greedy, you have to prove. The other part, we take it as a guess. If you advance in your studies, you're gonna be more formal about that. But in this class, if you decide it's not greedy, you don't have to make a proof. Okay, that is not greedy. So, is this one greedy or not?
No.
No. This is dynamic programming, so no proof. Okay. So how is part 2 looking like? Oops, I don't want to cover these two. I wanna write it here maybe. How is part 2 looking like? I have to write the recursion for rod cutting problem. So who's C, my objective? Max value, right? Remember, C is what I'm trying to optimize, minimize. Now, how many arguments, who dictates what are the arguments in here? Obviously, N is the argument, the length of the rod. What other arguments you decide to put in? I want a more philosophical notion first. How do I decide something must be an argument or not? When I move to sub-problems, that thing is different, right? So whatever changes when I move from a problem to sub-problems, I have to put it in the argument there. So what changes? N obviously changes, right? I'm cutting something, BLSN. What else changes?
Price of the pieces.
What?
Price of each piece.
I don't think the prices change. Prices are the same. Remember the coin problem? Did we have anything with the coins in C? Why? Because the coins were the same. How about here? Is that the same issue? The prices and the lengths, are they changing when I move to sub-problems? No. So I don't need other arguments because while this is of course part of the input to my problem, for different table I'm going to have a different output. In fact, we have here 2 tables and I show you guys 2 outputs. This is not necessary to be part of C as argument because it doesn't change when I move to the next problem. It's like a global variable. It's fixed in stone once I run my program. Right? So who's this? Since I can make the cut anywhere I want, it's easier to just make it after the first part, right? Because anywhere I make this cut, I have the optimal solution substructure. That's how we call this, optimal solution structure or substructure, optimal solution subproblem structure, however you want to call it. So I can decide for my algorithm where do I want to cut it. To make it easy, I cut it after the first one. So how do I write this recursion if I cut it after the first one? It's a choice here, right? So it's just cut L first. Right? If I cut the first piece of size L, because I'm making the decision boundary after one piece, what would be the value? L, or its price range? Price of L. Plus, what is the subproblem? C of, right? Because that's the best I can do in here, and minus L. Now, there's some version of this problem where it says each cut takes 1 unit of the wire. The cut itself, the blade, when it cuts, that's typically true not for metal, but for wood. People who do carpentry, they need to account for every time I'm cutting the wood, there is a 1 millimeter or 2 millimeter that the blade cuts out. If you ever, anybody does carpentry here? No, you should try that. Try to put a cabinet together. If you don't account for the cuts, cabinet's not gonna come out right. You have to know what blade you have, and that blade is gonna take, depending on the blade, so much. So if each cut takes 1 unit, how would this thing change? N minus L minus 1, if I have to account for the cut. But we don't have that in here. Okay? So I have this recurrence here. And what is now the solution table? How many dimensions I need for the table? 1 dimension. This is the solution, the subproblem table. Why is it 1 dimension? Because I have this n, right? So when I'm looking at this, now the problem is I don't know where the cut is, right? So that was our guess here. Is it greedy or dynamic programming? Greedy will mean I can decide the cut before solving the subproblem. Dynamic programming means you have to solve possibly many subproblems before you decide. That's the main difference computationally between greedy and dynamic programming. They work on the same kind of subproblems. The difference is in greedy, we make a decision. So we only need to solve the subproblems that are necessary. We should write that down. Only solves necessary subproblems. This solves many subproblems. Some not part of the solution. So it's possible that in dynamic programming I solve some subproblems, but given the result, I decide not to use them. Right? So that's what's going to happen here. How do I look for which piece to cut? Since we decided dynamic programming, it means I can't decide it until I actually solve the subproblem. So I have to do something here. How do I search for the proper L to cut? This formula is true if somebody gives me L, right? But I don't have L. I mean, L means deciding where the boundary is. So what do I do? And then I take maximum, right? Maximum over all else in the set length of price of L plus that, right? Now I say here L in set length, remember, set length may not be all 1, 2, 3, 4, 5, 6, 7, 8. Maybe the pieces that I can sell are 1, 2, 5, and 7. And then that's the acceptable length. Cutting a 2-piece that's not sellable is not useful to me. Right? And if I have that, I may have a waste at the end. I may have something that I just can't sell. Okay? So I have a max here. Usually this max in a recurrence, it's a pretty good indication of dynamic programming. The fact that I couldn't make a decision, I have to try several things to decide which subproblem it is. It's usually an indication of dynamic programming. So now, here's n, right? That's the problem of n. What subproblems do I need to solve first? Who's this? N minus L1, N minus L2, N minus L3, so on and so forth, right? I need to have solved this problem because I don't want to do it recursively. I need to say the subproblems are already solved when I get here. So when I get to problem n, I need to have these other subproblems already solved. And in dynamic programming, typically we don't bother to say, is it possible that there is a subproblem? This is a not necessary subproblem. Ever. As in, this particular subproblem, while it's in my table, I will never need to solve it. Is that possible, theoretically? Maybe. We not bother with that. In dynamic programming, there might be some problems that theoretically are invalid problems, like we don't have to really solve them. We don't care about that, we're just gonna solve all of them. In greedy, what's the deal with greedy? Since we can, this is what this max does here. It says you have to choose one of those, right? The max is saying, once you solve all those subproblems, choose one of them, right? The advantage of greedy, if you can make the greedy choice to say, this is the one I need, you would only solve that subproblem. Right? How many people would you? Good. If there is one problem that's not necessary, greedy won't solve it. Because greedy can go recursively, make a decision, solve only that subproblem. Make a decision, solve the next subproblem, so on and so forth. Greedy will never step on this spot. But dynamic programming, unless we want to be very fancy, we'll just say, figure out the order of the subproblems here, and just solve it in order. So that when I get to a problem, I have the subproblems already solved. So the order of computation is which way? Left to right, right? So this is the order. Okay. Now this is a very simple pseudocode. It's like the coins. It's part 3. How do I do this? C of 0 is 0. Okay, I can't sell anything if I don't have the wire in the store, right? And then for n, n equal 1 to big N. Okay, this is the big N here. Right? I have to find the max, right? So I set the max equal minus infinity. And then I check all the wires, right, that I can cut. I figure out the max, so I'm computing the max. How do I do that? In pseudocode, I could just say max. So a version of this could be saying C of n is exactly that. Max over all else of price of L plus C of n minus L. That's acceptable for pseudocode. Max is a very simple function that you don't have to explain what it does. But I'm going to write it explicit here. I'm going to say for L in length, if max is currently smaller than P of L plus C of n minus L, right? Do what? Update C of n. I need to put C of n is P of L plus C of n minus L. Right? So I'm trying to, this is a version that just says max direct. I'm computing max in here manually. That's a if, that's a for. And then I'm going to say return C. Is that correct? Is that going to find the max?
No, I haven't said it.
Hmm?
Update the max.
I have to put it here somewhere, right? Where is the max going? Where do I say C of n in here? I think outside this loop, right? C of n is all right. 6th grade pseudo. It's important to wake up early in the morning. Now, if I want to add tracing, right? So this is going to give me the max or not? Is it computing properly the max given the subproblems? Can I get the proper max here? Yes. Right? But I need to trace the solution. The solution is not to output the maximum value, $25, or $22, $24. The solution also have to output what are the pieces that are being cut from the wire. Right? So if I want to print the solution, I need to track it somehow. Right? So I need to say here, update S of n. That is the tracing from, if you want to solve problem n, which subproblem do you need to point to? So how do I do this? Which subproblem? This max got updated because I found a better subproblem to solve, right? So what's going to go in S of n? N minus L. Right? It's saying if you want the optimum for n, you need to, they need to cut a piece of size L. So I could either store n minus L, the subproblem, or I could store L. What piece of wire I need to cut first. So now, how do I trace the solution? That's part 4. I start with n, right? And I say, what's the first piece that I need to cut? Print, which is the first piece? S of n. Right? That's the first piece, that's why I'm tracing it, that's the piece I need to cut. And then, how do I update? I make n equal? And I do this while n, you guys have to figure out the condition here. Yeah, it's 0, but not if I have a waste, right? If I have, you can say, well, n bigger than 0, this is not going to work if waste is possible. Right? Because I may end up with a little waste that's not, I don't have a tracing for it, and then this printing won't work. So you got to figure out that how it actually works, if I may have a waste. All right, but this is printing the part, and then it's saying, move to the next subproblem, n minus the part, and then keep doing it. It prints all the cuts. Okay. How about the running time? This is a O of n loop, and this is a O of L loop. So it's roughly n times the size of length. How many lengths are given to me? Usually this is a fixed table. Maybe the lengths are 1, 2, 4, 8, and 16. Like typically in Home Depot, things are going in like a certain denominations. Right? Okay, so we have the road cutting problem. Now, when I write pseudocode, I'm more informal than the book. Like C of 0 equals 0, I don't say how long C is, I don't initialize it, da da da. Usually the book is more formal. I'm talking about the Corman's book. I'm not requiring you to be more formal. If you write this and it's correct, you get the full credit in this class. But it'd be useful for the ones of you who think of you more like a problem solver, algorithms, more than programmers, to know how formal pseudocode is written. Because when you get a job, if you have to discuss a solution to somebody else at the same company, you can't write your own version of pseudocode. We do that here to emphasize thinking more than formalism, because that's essential. But if you are really supposed to write pseudocode to detail a solution that you've done, you're going to have to be more formal in your job than this. Okay, next up. Next up. Yes.
So in this rod cutting, like we can use sort of a greedy approach also, right?
I don't know.
You can take the ratio of price versus the length and sort them. So it will give you the most valuable length, and then based on that you solve the problem.
So it's diagonal.
Yeah.
So he's using the approach of the discrete knapsack that says if I divide, obviously as far as if you have an infinite wire, right? As far as long-term stores will go, selling the piece that's most valuable as far as price per length goes, it's the best way to make money. So that's not an unreasonable approach. But is that for a fixed wire, is that optimal all the time, no matter what the lengths are? Is that true for this table?
Yeah.
Yes.
What is the most valuable piece?
6.
17 by 6 is the most valuable?
Yeah.
Yeah.
And 3 and 2.
Okay. Is it true all the time? No matter what the lengths and values are, is it true all the time? That's exactly the problem you guys are going to have in the midterm. Given a bunch of things, and you'll be like, okay, I have a greedy strategy, right? That's obviously greedy. If I could decide, I sort the items by value versus quantity versus price, right, ratio, and I pick the best one, that's a greedy strategy. Why? It makes a decision before solving the subproblems. You're saying pick that item, cut that piece of the wire, without worrying about the rest of the wire, what's going to happen with it.
We can do a bit of dynamic approach in that, then
I have to be very careful about that, because my intuition here is that greedy doesn't work.
It doesn't.
Do you have an example?
Yeah, for 4, if we take, we'll have to consider 2 and 2, that gives us 10.
Wait, what?
For length 4, and if n is equal to 4.
Yeah.
So we'll consider twice, 2, so we get 10. We'll cut it into 2 halves,
Yeah.
so we get a 10.
Yeah.
But if we go to solve it by greedy, we'll probably add 3 and 1.
Well, let's see, what would be the greedy choice for n equal 4? Obviously, I can only look up to here, because the other ones won't be allowed to be cut. What is the biggest ratio up to here? So 1 to 1 is 1, this is 2.5?
And that is 2.6.
This is
Around.
2.6?
Yeah.
You sure?
Yeah,
2.6.
And this is
1 again. Sorry, 2.25.
2.25?
Yeah.
So what he's saying is saying if these are my choices, 1, 5, 8, 9 for 1, 2, 3, 4, the greedy choice will be
3.
2.6.
Yeah.
Is the biggest ratio of value per quantity, right? So you see the greedy choice is these 3, which obviously gives you the 1 as the remaining piece. But that's not optimal because you make $9, 1 plus 8. Well, you could have made $10. Very good, right? So the difficult problems in this type of problems, so this is dynamic programming, and it's always dynamic programming. For some denominations, some lengths, and some values, greedy works. You saw the coin change that you had. This is a very similar problem. It doesn't maximize n, it minimizes the number of coin. But we could have formulated the coin problem that way. What's the way to maximize some number of cents that you can give with a set of coins. The difficult question that's not in the scope of this class is for which kind of denominations or lengths and prices this is a greedy problem. Now, in general, that's a hard question, but for a specific set of denominations, like say, if those are exponential, then you can use greedy. You had this problem with the coins, right? That says if the coins are geometry progression, you can use greedy to solve it. So I think that's okay. You can expect such a problem. Here's a set of denominations or lengths or values. Can you do it greedily or items in a knapsack? But in general, deciding which denominations or what items allow a greedy solution and which ones do not, that's not an easy problem. Okay, let's move on. Here's my next problem. N choose K. You guys know N choose K? What is it? In English. Number of ways to pick K items out of N. Of course, mathematically, that is the number of right, but mathematically is what? If I have a set A of A2, AN objects, this is the number of combinations. But that's combination in mathematics. So I'm asking for number of subsets of a set N elements. These items here are not numbers, are whatever objects, people, diseases, hospital places, doesn't matter. The number of how many ways can I choose K of them is fixed, right? It's based on. And there is a formula for this, which we're not gonna use today at all. Anybody remembers the formula? There's an actual mathematical formula for this. N factorial, K factorial. So we're gonna pretend we don't know that formula, because if we know it, that would probably be faster to compute it that way, right? So the only thing I want to add here as a parenthesis, not related directly to the solution of this problem, in combinatorics, you got to be very clear of differences between sets or subsets and sequences. What is that difference? Sequences are order. So when I say sets, I mean the order doesn't matter. A1, A2, A3 in any order is the same set. When I say sequence, in different languages this is not necessarily called sequence, but there's a difference how many sequences I can obtain. That is A1, A2, A3 can form different sequences, and then I have something to do with permutations and how many ways I can rearrange the objects, right? But we're asking simply here for subsets. So how do we think of this problem in a divide and conquer sense? So suppose you have to compute N choose K with a computer, and you don't know that formula of the factorials. You forgot it. What do you do?
Choose maximum number of ways that we can choose one item from N. We add all of them.
Brute force. You try all possibilities of choosing K, and then you count how many there are. I think that'll be extremely inefficient. That doesn't rely on dynamic programming at all. Right? So by the way, there's a notation for this. You guys know it? N, K, like this. Other countries use something like C of NK, but we use the American notation here, NK. So N choose K with this parenthesis, no bar in the middle, is the number of ways picking K things out of N. And I want a dynamic programming solution, not a brute force. Try all the subsets and count them. So how do I think? I'm going to do 1, 2, 3, 4, the parts. This is not a difficult problem. It's the same the reason might be difficult because you'd be like, oh my God, aren't you scared? I remember that was very hard when I was in high school. And don't worry about that. Think about dynamic programming. How is an optimal solution gonna look? Well, what is this? This is a number, right? It's the number of ways of choosing it's an integer. It's like 17,765,432 or something, right? So how do I think of the optimal solution? That's a number. The optimal solution is a number. I have to think of, this is a number, n choose k, but I have to think of a number of ways to do something, right? I want to think of this as a number of ways to count things. If I only think of it as a pure integer, it's hard to break that integer into a sub-problem solution, right? But if I think of number of ways to do something in a counting sense, I could say count that, and then count that, and maybe add them up together, or subtract them, or multiply them, or something, right? And once I decide, okay, the number of ways I need to count the students in algorithm sections, there are how many sections? 4 sections? Well, I can count section 1, count section 2, section 3, section 4, add up the numbers, right? That's kind of a divide and conquer principle. So that's how I want to think of this. Number of ways to do stuff. So this number of ways, if I look at this set here, to number of ways to pick k out of, let's put the set here, A1, A2, AN. So what I'm going to do, I'm going to say, I want to split this into 2. I want to make a partition. A partition in counting means I'm looking at all the ways to do something, and I'm separating into the ways which has one property and the ways that do not have that property. If you want to think of students, I can think of males versus females, right? I want to count the males and count the females. You really want in a partition to be all items with property P versus all items without property P, to make sure it's actually a partition. A partition is not counting everything twice, but make sure you count everything once, right? If you design properties, let's count all Indian students, let's count all the Chinese students. There's a danger that you miss a country, right? You miss some country, like you make a list of the countries you have in mind, and then you don't count everybody. If you count people by, say, skills, say people who did programming, people who did that, the problem is you might overlap. You might count people twice because maybe a person has 2 skills. So you got to be very careful when you count things to make an absolute partition, if that's your intention. If you overlap things, if you have to overlap your things, then how do you count when things are overlapping? It's not a partition. In a partition, it's easy, right? Once I partition my items in these ways, in this problem, items are ways of subsets, right? If I make a partition, I just count each chunk, right? That's easy because they don't overlap and I'm counting everything. When I'm counting and there is overlap, what do I have to use? That has a name, right?
Union.
Yeah, but it has a name, that mechanism. It's called inclusion? Inclusion-exclusion principle that says if you count things that are overlapping, you have to subtract the intersections of 2, add the intersections of 3, blah, blah, blah. So it's much better to not worry about that, to make an absolute partition from the beginning if you can. So that's what we want to say here. I want to partition the number of ways to pick k things. Again, if you have trouble with the mathematical, and I've seen that a lot in computer science, people are smart, but they just don't think abstract mathematics. Think about, I have 40 students, and I want to pick a team of soccer players of 10 people. In how many ways can I select 10 people out of 40 to make a soccer team, right? So how can I partition this in a way that makes it easier to count? Partition, I'm looking for a partition in 2 sides, such that every subset, every way of getting 10 out of 40 goes either there or there.
Chosen and not chosen.
Choose what?
Like if you have to choose a player
Right.
We choose one player at a time.
So the partition may be on A1, but for some hidden purpose I have for class today, I'm gonna choose AN to make a partition. I can choose any player. So I say, here's a partition. All the subsets that contain this last player, and the other ones are the subsets that, you guys know this sign? Is the belonging to, just, you can read it backwards, AN belongs in here, right? Is this a partition? Is every set that I'm counting either here or here? Yes, because you either contain that or don't contain that. And am I counting anything twice? Is it possible for a subset to be in both places? No, that's definitely a partition. So then I say, what you're trying to count, you can count separately all these subsets. Of course, the size of the subset has to be K, and the size of the subset has to be K, right? So I'm still counting the subsets of K elements, but either with this property or without this property. AN could be any particular element. I just use the one that's indexed last, makes it easier to think about. So if I'm counting these elements, what do I want to say here? What's the optimal substructure mechanism? How do I think in terms of dynamic programming? For this problem, it'd be a lot easier to jump to step 2 to write the recurrence first. That is true. But suppose you don't know that. Suppose you don't know, like if I show you step 2, it will become obvious what the recurrence is. I bet you could write it probably without doing step 1. But where is this optimality hidden?
If you consider, like if we have only A1, then how many, in how many subsets we can divide in? If we have A1 and A2, how many subsets we can divide in, and so on we can go for.
So if I take A1 and A2 as a set,
So this is n K for us.
so you're saying break it here.
Yeah, and anywhere we can.
So the problem is the optimal solution refers to a number, while the sets are subsets of K, right? So this is a subset of K, that's the things that I'm counting on, right? So how do I say this part to the subproblem? I mean, you guys, I'm gonna let you guys think about that for a second, and I'm gonna step to step 2 here. I'm gonna say, I know how much is this and this. We'll get back to step 1, but how many subsets of size K contain this element AN?
The number of subsets that you can form K minus 1, like choosing K minus 1 elements apart from N.
Very close. He wants to say the number of ways to choose out of the remaining N minus 1, K minus 1. So this in here is N minus 1, choose K minus 1, right? Because this is the number of ways to choose the remaining K minus 1, remaining because I already have this one in. Remaining K minus 1 out of the set A1, A2 up to N minus 1, right? Because I already choose N. How about here? If I say AN is not included, how many ways can I choose now K items if AN is not allowed? N minus 1, that's the remaining elements, choosing K. Which is in English, number of ways to choose all K, because AN was not allowed here, out of A1, A2, up to AN minus 1, right? So what's going to be the recurrence then? N choose K. Since it's a partition, right, it means I can put it back together simply by adding the counts, right? I'm saying you counting something, you can count it here, count it there. So what is this? Anybody remember this formula from high school? How is it called? Sometimes it was Pascal triangle. These binomial coefficients have followed these rules, right? This is the same as dynamic programming. Okay, so I have this recurrence. I'm going back here. What is the optimal solution structure here? What is that saying? Okay, in English, what makes this solvable by dynamic programming or greedy? What makes it a divide and conquer problem? Like the way you said it the first time, you say try all the subsets, right, and count them, right? If they have size k, they're good. That's a brute force solution, right? It's not a divide and conquer solution. What makes this a divide and conquer solution? You have to have this substructure, some sort of substructure property that's hidden here. What is that?
Because they're not overlapping.
What?
Because they're not overlapping.
Overlapping of?
Yeah, those two counts are not overlapping.
Right. The optimal solution substructure comes from the fact that I can split it into a partition. And each part of the partition is actually a problem in the same form as my original problem, right? If you look at this, is exactly counting how many things I can include with k minus 1 elements here. That's certainly a subproblem in my table, and this is the other subproblem. So the optimal solution structure is the fact that my optimal solution can be broken into this part and this part, and each of them are subproblems. Now, where is that decision boundary exactly when I say break it? Before we have this nice wire, so break it was like between the parts. Now,
Number of choices.
Every element.
what am I actually breaking?
Number of,
Am I breaking the set? No.
No.
What am I breaking? What am I splitting here? The counts, right? So if the optimal solution is a count, right? There is a break in that count such that this represents some other count. This is a subproblem. And this represents some other count. And those subcounts are this part, choosing AN or not choosing AN. Now, is AN important here, which item I'm picking? I could pick the first player, the second player, the third player. This is not the biggest or the smallest, it's just an ID. So I have this new feeling, these kind of problems, combinatorial problems, have this out of the blue feeling. If you don't know about it, you'd be like, wow, what just happened? You pick in this AN, and somebody says, no, pick A5. And you're like, how did you pick A5? Well, it doesn't matter, I pick one, I fixed one, the first player, the last player, the middle player. It's not sorted by, it's not like in activities where we had the reason to pick the activity that was finishing last, right? Or in these greedy choices when they work, pick the one that has the best ratio. That was dictated by a greedy or some sort of things that make sense. In here, picking one element have nothing to do with any strategy. It's just for the purpose of breaking the counts into two parts. Any element would actually break it into the same way, right? It doesn't matter what element I pick, I get the same formula, right? Because the elements are in here just IDs. There is no bigger, smaller, greater, more valuable. They just 1 to n elements, players if you like, right? We don't have anything that says this player is good or bad, or is more valuable, or is gonna score more goals, whatever. We don't have that, they're just IDs. So picking one of them, it's as good as any other one of them for the purpose of breaking the count into the subsets that contain that player and the subsets that do not contain that player. So you guys can try to fix all this part to see how that plays out for a combinatorial problem. Now what's the computation table here? So if I write it as C, of course, I'm going to write it this way, right? Recursively, it's going to be C of plus. So who's changing here in terms of these arguments? N and K. So I need how many dimensions table? N, K. Right? So here's I have a problem. This is the problem NK, right? Where does this subproblem depend on? What other subproblems I need to have? Where is n minus 1?
On the same line.
Here. Right? This is n minus 1 k. And here it's n minus 1. So the arrows go, I need this problem, I need this problem. And is it one of them or both? I need both. This is not choose the max, choose the mean, figure out one of them. It's do both of them. So how do I write the code? C of n, C of any n, I'm going to say all n 0, the number of subsets with 0 elements forever for any n is 1, right? Which is the, what subset is the one that has 0 elements? The empty set. And then I have to say C of all, let's say 1 to n. This is a comma here. C of 1 to n and 1 is 1 to n, right? Because C of any item I should write it more computer scientists, I, right? So this is for all I, 1 to n. It's a for loop, but I'm skipping the for loop here. I'm initializing, right? Because choosing one, in how many ways can I choose one out of anything? It's how many things are in the set, right? And now how do I write this for loop? For n equal to 1. Right, so where do I start? I start at 2 to max n, say big N. And now in what order do I, so I start at n equal 1. Do I have n equal 1 here? So what did I just compute? I computed if this is 0, right? What did I compute in here? All and 0, I've computed this line. That's done, right? And when I say all and 1, I've computed this line. That's done. So now I have to start with n equal 2. I need all n's, I think, because I want to go to this line, right? So what is this line? That's k equals 1. So what do I do? 4. I need to go from 2 to n. C of nk is n minus 1 k plus n minus 1. And that's done, right? Just I'm not sure about those for loops. Are they correct? So when I move to n equal 2 right here, so n equal 1, that's not computed. Maybe start with 1.
For here,
N, then n equal 2, n equal 3. Because I need to do it column by column in here because I need those subproblems when I move forward. So it's gonna be this line, this line, this line. Maybe I needed this a different initialization here. So everything. How about you guys fix this? Can you fix this code to make it work? I don't want to think about it right now. I've done it when I was in 9th grade, so it seems hard now. Right? Okay, now this is a little stretch. Is this dynamic programming really in the sense of the book? Perhaps not. If you say this dynamic programming, people might be like, okay, I never heard of this dynamic programming problem. It's true, this is not written as dynamic programming. But what I want to emphasize here is that the same kind of thinking works in this problem. In combinatorial problems, you can think of them as recurrence into sub-problems. In fact, most recurrences in most combinatorics rely on something like this to be efficient. Otherwise, it's back to brute force, trivial subsets, exponential solution. All right. Now, what do we actually want to output here? At the very end, we say what? Return C of nk, right? Do we need to trace anything? Because we want to output a number, right? We don't need to trace the sub problems and such. That's why this is not considered a standard dynamic programming question. So the last one that I want to do today is the discrete knapsack problem. I already said last time and the time before why the discrete knapsack doesn't have a greedy solution, right? We picked those, if you look at the notes, there's some examples to whether you pick, what are the three greedy choices that make sense. So we have a Z, that's the max weight for the knapsack capacity. We have weights, and we have values. So the goal here is to pick a subset of items such that the sum of weights has to be almost Z and maximize the sum of values. Same problem like before. And what are the obvious greedy strategies one could try? The biggest value, the smallest weight, or the biggest value by weight. And I think there's some examples quite easy to find where none of these strategies work. In fact, I think there was one on the board last time. So what do we do? Part one. What is the optimal solution going to look like? If somebody gives it to me, what is it? what would be in that optimal solution? A bunch of items, right? This would be item 1, item 2, up to some item k, right? A solution means a subset choose this set of items. Let's write the weights here, but of course we have the values too. So how do I think of this optimal structure mechanism? Here's the weights, right? And maybe in the knapsack, there is something, a little bit of extra space, right? It's possible that if you put items in your knapsack, you may not optimally, if you want the maximum value, that doesn't necessarily mean you're going to fill all the knapsack, because it doesn't have these nice denomination properties that no matter how you cut it, you still can sell the remaining. Right? If those are random weights and values, it's possible that they won't fit necessarily. So, like before, if we are to break this solution between the weights, this has to be optimal, and this up to here has to be optimal. Well, there's a trick, right? This has to be optimal among all items, and this has to be optimal among all items without those. Why is that? Why is that different than in the coins problem? When the coins problem, why didn't we exclude the previous coins? There was what? Unlimited coins. I could use the same coin again. This is not like that. Every item is exactly once. So once I put it here, I can't put it on the other side. That's going to create a problem. That's going to complicate things much more than the coins. The fact that if W1 gets here, it can't also get here. But the thing is, I can't completely separate those subproblems then, because I can't say solve this optimally, because I didn't know what item the other problem is going to choose, right? Even if somebody gives me the decision boundary here, God comes down to us and say, this is where you chop off your knapsack. Now you have 2 knapsacks. Can I solve this problem independently? No. Why not? Independently, both solutions might contain, some jewelry that's very expensive and very small. But that jewelry, there's only one, so I can't put it in both sides. So I can't just take these and go ahead and solve 2 subproblems of that size and that size, even if somebody gives me the decision boundary, which I don't have, of course. So there's a key difference between this problem and the coin problem. That if that is true, right, this has to be optimal within the set of all items, and this has to be optimal into the items minus I1 and I2, right? I could think of it backwards. This is optimal on all items, and this is optimal minus whatever items are here. Are we all on this page? That these have to have this optimality. In this sense, if there is a better solution for this that does not include W1 and W2, so it's valid, exchange argument, I could put those items in my knapsack. I get a better knapsack overall. Better here means more value. Weights are a restriction of how much to feed, right? So we have this additional wrinkle to the coin problem that we can't solve the problems independently because any item that goes in one cannot go in the other side. But other than that, I think it's optimal, right? This is step 1A, and 1B is saying what? If you know the decision boundary, and if you fill this with any items, and you manage to fill this optimally with the remaining items, that overall gives you an optimal solution. And part 1C is it greedy? If we couldn't find the decision for the coins, which were infinite, so we don't have the dependency between the subproblems, it seems unlikely we're going to find it here. Right? So dynamic problem. Okay. Let's move to part 2. What's the recurrence? Yes.
In the first part, we cannot write proof for this, right? Like it is more of intuition. So
This?
the first one, like
The first one, if you can solve this optimally, and then you can solve this optimally only with the remaining items, isn't that an optimal solution? That's your question?
No, like I was asking, while writing a solution, we directly write that we can.
Yeah, you have to explain the mechanism. You don't have to prove it mathematically. You just have to explain, if I look at the solution, the chops are between the weights. The chops are not between the values here. Why they are between the weights?
Because we have the maximum.
Because the knapsack, if you look at it as a volume or as a physical thing, it chops into weights, into capacities, right? Think about a truck with like 2 compartments. It's how much can I put in that compartment versus how much can I put in that compartment. So you have to break it by weights. Right? Yes, you just have to explain it. There's no formal mathematical proof here.
So, in this, the right side, why are we talking about optimal only in the area that is filled? It should be optimal in the entire area left, whether something is empty or not.
You mean like that?
Yeah.
Very good.
No, I
So
think-
he's saying this has to be optimal up to here, because if I find a better solution that doesn't fit into what you have but takes a little bit extra of what I can do, that would be better than true. So how's the recursion going to look like? Z obviously goes in here. Do I have to include some tracking of the items? For the coins, I didn't have to, right? The coins, why didn't I have to include anything with coins? I moved to the subproblem, the coins don't change. They're the same coins. In here, they do change. So I need some sort of item set. I'm going to leave that vague for now, because I want to deal with that later on. But clearly, I need a parameter for the item set, because if an item is chosen to be cut or put in, that item is not available later on. In the subproblem, it won't be available. That's exactly this dependency. I need to keep track of what I'm already putting in the knapsack. Okay? This is what? This C, the output is what? Max. Remember, C, it's always objective, so I'm trying to maximize the value here. By the way, previous meter, use a variant that says minimize the remaining space. A simpler problem because values are irrelevant for that, right? If you're just trying to minimize the remaining space, you don't care about the values, you just care about how much space is in here. Okay? So this is, since this chop can happen anywhere, just like with the rod cutting or with coins, I'm going to prefer a chop that's after the first one to just make it easier. So I'm going to say here, choose item I. If I make the cut after the first item, what's going to be here? So the remaining problem is Z minus WI, and the item minus I, item set, it has to take I out, right? We know that because it's this dependency that we just talked about. And it gets the value, right? Because once I put the I in the knapsack, I get the value for that. Of course, I don't know how to find that value. I don't know where the cut is. If somebody will tell me your cut is 75 units away, then I know to find the weight that has 75. If there's multiple weights of 75, I pick the biggest. That'd be easy, but I don't know where to put this cut. So what do? I search for it. I have to look for which is the best element to put in, such that it gives me the maximum overall value, assuming I get that element, plus the remaining subproblem, right? And I have to keep track of these items here, because if I don't keep track of them, I'm back to the coin problem, where I could use an item as many times as I want. All right, what's the computation table then? There's a Z, obviously, and there is the item set. And if I have a particular problem, that's a Z and an item set, where are the subproblems that I need to have solved already? I have to, if I take the item, the WI out, Z is gonna go down. So here, who is this? Z minus some Z minus some weight, and the items minus set I, right? So that's one, but I may have another one that is a different item, right? So I may have here, let's say this is item 1, I may have another problem that is Z minus item 2, the weight of item 2, and item set minus, I could have this problem, of course it has to be a little smaller, right? Or I can have another problem that is Z minus W item 3, item set minus item 3, right? I could have this problem. Now, is it true that Z always goes down? Yes, because each one of those are Z minus something. So at least this way, it always goes down. That means if I fill the table, if I have all the previous rows filled here, I'm going to have all the subproblems. The problem is they're not on a particular, they could be anywhere in the table. How about this way? Do they always goes left?
Yes.
That's tricky. It always goes left if you manage this item set properly. In other words, this is the item set I. When you guys says it goes left, it means for any item minus I3 in here, and this was item minus I2, you're saying all these have to be on the left side. I'm saying that's not an obvious thing. How do I manage the Z to make sure Z minus something goes always down? That's easy, right? Z is what? It's going to be a bunch of integers or something, right? A bunch of ticks, right? 1, 2, 3, 4, up to max. So how do I know? This is a number, right? How do I know it goes down? It's Z minus something, so it goes down. But this is not minus something. How many item sets are there to consider? Right? It's not easy to say, write all the item sets. Can you write all the item sets so that they have the property that the left side is always the minus one? I think you can. You write all the sets of size 1, then all the sets of size 2, or sets of size 3. In that way, if I set sets of size k, anything minus that will have been written before. But that's another problem. How many item sets I'm going to have here if I do that, if I write all the possible item sets? 2 to the n, too many. Right? That's an exponential solution right there. So can we manage these item sets somehow to make it nice? Yes.
Like, I don't understand why are we considering item sets here? Cannot we consider just one item at a time?
Yeah, we can. So that's why we can solve this problem. But which item? So he's saying you don't have to look at all the item sets, right? All of them. There is a way to kind of go over them nicely. And that's the reason we did this problem before. Remember what happened here? We picked one. Now we didn't pick the biggest or the smallest. So I say we can do the same thing in here. I say we can order items randomly. I want to super emphasize randomly, as in it's not by value, not by weight, not by ratio, nothing. It's nothing to do with strategy. I'm going to say item 1 is before item 2, before item n. So I pick an order. by student ID. And now, I want to think like in this problem. When you choose items in your knapsack, you could choose AN or not choose AN. Right? The way to maximize your knapsack is either by choosing that particular item. Again, that's not the largest, smallest, biggest, heaviest, nothing. It's just one of them. I pick one of them random, right? So if I think about it that way, what is this item set then? If I sort these items by a random but fixed order, the item set IK is going to be the items I1 up I2 up to IK, right? So this item set becomes who here? The original problem. That's the whole. That's the all items. So what is that? That's IN, right? It's all of them. And in here, what item? How do I say choose item I? So let me leave this like that. Let's rewrite that recurrence, then we're gonna break up. C of Z and item says that who is this? This is item 1, item 2, up to item N, all of them. Now I think like in the previous problem, you can either choose the last one or not choose the last one. So I'm not gonna search like with a max. I'm just saying you have two possibilities. Choose the last one, not choose the last one. So it's still a max, but it's only between two options. If I choose the last one, what do I get? Choose item IN. So in that case, I get value IN plus C of Z minus WN and I, what is this? I'm C of Z minus WIN and I who? N minus 1. This is what? This is all the items to N minus 1, right? Now if I don't choose IN, what do I get? Not the same. Do I get any value? No. I get C of, I still have the whole knapsack. It's easier to think of this once you understand the previous problem. The counting part. Why is it that in here, this is a little PhD level, why is it that in here, where the items are clearly not like the players before, right? Players didn't have weights, didn't have values, didn't have nothing. In here we do have values and weights. And yet, we can pick an item, IN, which was a random order, right? I randomly sort this in, I didn't pick an order based on anything. Why can't I pick that IN and say either pick it or not pick it and still works? We gotta talk about this more next time. But I think the rest is easy. Once you do this, what is my computation table? The problem I had here with the item sets doesn't exist anymore, right? This is gonna be I1, which is only item 1. This is I2, which is I1 and I2. And the last one is IN, which is I1 up to IN. And the previous one is IN minus 1. This is linear now, right? I don't have this problem with exponential number of subsets. The question for you guys is, why does this work? Why in the end it gives me still the optimal solution? If I pick, I pick from the very beginning item 3 and I say you can either pick it or not pick it. Move on. All right. So we have to break up here. There are 2 dynamic programming homeworks, right? So we need to have this done by the midterm. Everything, the midterm will be everything up to dynamic programming, the last week. So next week it's still dynamic programming. And after that, before the midterm, we're going to talk about other things. But those other things are not in the midterm. So your job by the meter is to prepare on dynamic programming. I would expect nobody would start the next homework. That's why it's due after the spring break, because no one will start hashes and trees while the meter doesn't contain those.